Hey guys, in this video we're going to talk about Chapter 14, Section 4, Gradients and Directional Derivatives in the Plane. Okay, so last time we talked about partial derivatives with respect to x and with respect to y. So basically what we were doing is we were finding slopes at a certain point on a surface in the x direction, so partial derivative with respect to x. And then we were considering slopes in the y direction as well. So we talked about those two situations here. Now what we're going to consider in this section is an arbitrary direction. So not just the x and y direction, but the direction of a unit vector, okay? So, alright, so as I just said, now we're going to consider the slope in the direction of any unit vector. So suppose we have this surface in purple or blue or whatever, and we have this point on the surface, and we're trying to figure out what the slope of the tangent line to that point is in the direction of this unit vector down here. Okay, so notice that the plane that we have that intersects the surface that's made with this unit vector is not parallel to the x or the y plane. It's just some random unit vector. Okay, so let's try to build our definition for a directional derivative with a picture. Alright, so the idea is that we're trying to find the slope of a function, in particular a surface, right, at the point FAB. So we're trying to figure out what the slope of this point is. That's the whole thing. That's what a directional derivative is. It's just the slope of a tangent line to a surface at some point, okay? So we want to find the slope of this function at some point in a specific direction of a unit vector. So we have some random unit vector that's laying on the xy plane, okay? So we can see it right here. This is our random unit vector. And because it's in the xy plane, it has an x component u1 and a y component u2, all right? So what we're going to do is we're going to consider a point on the xy plane first, P. So we're going to consider this point to be P. And what we're going to do is we're going to work downstairs in the xy plane, and then we're going to sort of project our results upstairs on the surface, okay? Okay, so here we have P, right? And so P is at A, B, 0, right? Because it's on the xy plane. It doesn't have a 0 component, and it's straight down from this guy. And so let's say that this point right here is Q. So let's say this point is Q. And that Q is going to be HU away from P, right? So HU away from P. So what does that mean? Well, what is HU? So HU, if I multiply this, the left and the right side of this U vector by H, I get HU1I plus U2J. And so that H can distribute there, and we get HU1I plus HU2J. So the displacement, we have x component, HU1, so that's going to be this guy right here. This is in the x direction, HU1, because we're parallel to the x-axis. And then we're going to have a y component of HU2, so that's going to be parallel to the y-axis right here. So that is my my y displacement, okay? So if that's the case, then my Q is going to have the following value. So it's going to be at, so the x coordinate for Q is going to be at A plus HU1, right? Just the x component. Because we started at P and we traveled HU1 to get to Q in the x direction. And then it's going to have a y component of B plus HU2. And of course, the z component 0 because we're in the xy plane. All right, so we did all of that for the reason that we want to define the directional derivative just like we do in Calc 1 with a regular derivative. with the limit definition, right? Because what was the idea in Calc 1? So we had this curve, right? And we were trying to figure out the tangent line to a point. But to do that, the way that we constructed the proof is we had this point P and we had this other point Q, and we looked at the secant lines, right? We looked at the secant lines when Q got really close to P, right? So the closer that Q went to P, the closer their points were going to be together, and the closer the approximation of the actual tangent line. So that's what we did in Calc 1. We're going to do the same thing here, right? Because what are we trying to find? We're trying to figure out the slope. And so, this component right here, we want to figure out what the change in this component is, which we can see what the change is. It's h. And then we want to talk about the change in the height component, right? And we know what that is. So basically what I'm going to do is I'm going to project this Q up here to this point. And so this is just going to be the point f of a plus hu1, comma, b plus hu2. Okay? So I'm trying to figure out the change in the, we can think of it as our x value, but really we're looking for the change in this red base, which is h. We can see that this piece right here is h. That's the change there. And then the change from this height to this height is just going to be f of ab minus f of a plus hu1, b plus hu2. So this guy right there is going to be f of a b minus f of a plus hu1, b plus hu2. Okay? And so from all of that, we're going to get our limit definition of a directional derivative, right? So remember, we're just dealing with slope here, rise over run. So the change in the height component, like I just mentioned, is the difference between the two values, f of ab and f of a plus hu1, b plus hu2. And the change in the what we're thinking of as our x component is going to be this h value right here. So that's where we're getting that from. So all that being said, this is going to be the slope of f in the direction of a unit vector u at a point AB. So it's very important that you know exactly what this means. This is the notation, kind of weird notation. Some books use a capital D to notate this, capital DU-AB. But our book was like FU. That's what we're going to use. So anyway, this is the definition, and let's go ahead and apply it. Okay, so if you remember last time, we talked about the limit definition for the partial derivative with respect to x and with respect to y. Now, these are special cases of directional derivatives, right? For the partial derivative with respect to x, the direction is in the direction of the unit vector I, right? Because I is our x direction unit vector. And so what that means is that our unit vector here can be broken up in a 1i plus 0j. That's literally just I, okay? And if we apply our limit definition of the directional derivative, we have fu at AB. So this is, again, this is the slope in the direction of u at the point AB on the surface. This is the limit as h goes to 0 of f of a plus hu1. Oh, I'm going to run out of room. Let me write it over here. Okay. All right. So the idea here is that because our unit vector in the direction of the x-axis is I, that means that our x component of this vector is 1, our y component is 0, so u1 and u2 are both 0, and that means, u1 is 1, right, and u2 is 0, which means this goes to 0, and we can see that this is exactly the definition that we came up with last time for partial derivatives with respect to x. In a similar way, we can do the same exact thing for j, right? J is the unit vector in the direction of the y-axis. And so in this case, our unit vector would have 0 as the x component and 1 as the y component. Plugging in u1, u2 into our directional derivative definition, we get exactly the same definition that we used last time for the partial derivative with respect to y. Pretty cool. Okay, so let's do some computations. Now the proof, showing you what this stuff means with the picture, it's not, you should understand this, but we're going to be doing a lot of computations, right? And so we're just going to be using the definition here. So it says calculate the directional derivative of the surface at this point in the direction of this vector. Okay, so let me go ahead and write my definition here. So we have AB is equal to limit as h goes to 0 of f of a plus hu1, b plus hu2 minus f of ab all over h. Okay, the very first thing that you want to do is you want to find your unit vector. Find a unit vector in the same direction. Scalar multiples, remember that? Find a unit vector in the same direction as the vector given. That's what we need to do before anything happens, because if we don't do this, we're going to get the wrong answer. And you should think about why we need a unit vector instead of just an arbitrary vector in a direction. Why do we need a unit vector? That's an interesting question. So find a unit vector in the same direction as the vector that's given, I plus j. All right. Well, how do we do that? Do you remember how we did that? We took the magnitude of the vector that was given and then divided each component by that magnitude. Okay, so the magnitude of the vector that's given, I'm going to call it v, is going to be the square root of the squares of the components. So the components here are both 1, so we have 1 squared plus 1 squared, that's just the square root of 2. And therefore, my unit vector in the same direction as this vector that was given, all we're going to do is we're going to scale it back by a factor of root 2, right? We're going to just divide the components by root 2 so that we're in the same direction, but now the magnitude of my unit vector is 1 instead of root 2, okay? All right, so my unit vector, again, we're taking this original vector, we're dividing each component by the magnitude, and that's our unit vector. So remember, a unit vector has a magnitude of 1, okay? So now that we have this, we can continue with our problem. Now we have everything we need, because what this is telling us is that u1 in our formula is 1 over root 2, and u2 is also 1 over root 2. We also know that a is equal to 1, and b is equal to 0, and that's really all we need to plug everything in here, right? This is our point that we're interested in, so a is 1 and b is 0. So let's go ahead and plug in everything into our formula. So we have the limit as h goes to 0 of f of, okay, so we have 1 plus h times u1, so this is h times u1, comma, b, which is 0, plus h times u2. So this is minus f of a comma b. So if I plug in 1 and 0 into my function up here, my surface function, f of a comma b is just 1 squared plus 0 squared, which is 1. Okay? So that's going to be minus 1 all over h. And now I can simplify this out. All right, so let me erase some of this stuff down here. Okay, so again, you know, this f of whatever, this is your x and this is your y, right? So we're just plugging it into the surface function right here, x squared plus y squared. So we have 1 plus h over root 2 squared plus y squared, still the minus 1 all over h. Alright, so let me go ahead and FOIL this off to the side. Okay, so first, outer, inner. Okay, so foiling that, I get limit h goes to 0 of 1 plus 2h over root 2 plus h squared over 2 plus h over root 2 minus 1 all over h. And then these ones can cancel. I can go ahead and pull out an h on the top. Okay, so those h's can cancel. And then if I plug in 0 for h, right there, I get, let's see, 2 plus, so I get 3 over root 2 plus 0 over 2. Okay, I think I messed up somewhere. Let's see, where did I mess up? I wasn't supposed to get that. Let's see. Messed up somewhere. Let's see where I messed up. Oh, I know what I did. Classic amateur mistake. I didn't square this. You see it? Let's go back. Let's go back to this line right here. Okay. So, okay, so I'm replacing that with this 1 plus 2 h over root 2 plus h squared over 2, and I gotta square this, okay? So this is gonna be h squared over 2. Alright, now I think I might be okay. That wasn't right. Okay. So again, these ones cancel. Let's go ahead and maybe we can even simplify before we pull out the h. So I have 2h over root 2 plus 2h squared over 2, which just becomes h squared all over h. Pull out an h. So pulling out an h, I get 2 over root 2 plus h all over h. Those h's cancel, and now I can plug in 0 for h, and I get my answer, and that looks right to me. So 2 over square root of 2, or if you rationalize by multiplying top and bottom by root 2, you get 2 over 2, which is root 2. So that is my answer. What is this? What did I just find? We have to keep that straight. What did we just find? We found the slope. Okay, we found a scalar. We found the slope of a surface, this surface, at this point in the direction of this vector. That's what we just found, okay? So we just found a slope. All right, at a certain point in a certain direction. Okay, so I'm going to kind of go through this sort of quickly. What we're going to do is we're going to use local linearity from last lecture to come up with a better definition that doesn't involve limits. So, alright, so this is what we have. Our limit definition is equal to the limit as h goes to 0. Notice that we have the difference in function values. That's just the change in f over h. And the change in x is just going to be the difference in the x values, right? And so we got that to be hu1. Difference in y values is hu2. And so using our local linearity definition, we get that delta f is approximately the partial derivative with respect to x at AB times HU1 plus partial derivative with respect to y at AB times HU2. And when we let h go to 0, this becomes exact. Okay, so this is another definition of our directional derivative that doesn't involve limits. So it means the exact same thing as the limit definition, right? It's just, I would use this definition because partial derivatives are fairly straightforward. And yeah, so that is that. So let's go ahead and use that definition that we just found to compute the directional derivative at 1, 0 of this curve in this direction. Okay, now we already know that this is the unit vector, so we don't have to do any work there. Our definition said this. It said that the directional derivative is going to be equal to the partial with respect to x, AB, u1, plus partial with respect to y, AB, u2. All right, so first of all, u1, u2, that's the components of the unit vector u. So u1 is going to be 1 over root 2, and u2 is also going to be that. Now the partial derivative with respect to x, okay, so we're treating y like it's a constant. So the partial derivative with respect to x is just 2x. Partial with respect to y is just 2y for a similar reason. And if I plug in, so we have a is 1, b is 0. If I plug in 1 here and 0 here, right, that's my x and my y, I get 2 and 0 respectively. Okay, so let's go ahead and use all of this here. We have fu1, 0 equals, okay, so the partial derivative at the partial derivative at 1, 0 is 2, so we'll just replace that. u1 is 1 over root 2, replace that, plus partial derivative with respect to y is 0 when we plug in 1, 0, and then u2 is 1 over root 2. So this clears, and we're just left with 2 over root 2, which again is square root of 2 if we rationalize, which is exactly what we got with the limit definition. Alright, let's go ahead and do this one. So we want to find the directional derivative. We have a surface, 2 variables, and u is the unit vector given by the angle pi over 6. Alright, well we actually need components for this unit vector to use our definition. Alright, our definition says that this guy is going to be equal to partial 1, 2, u1, which we need, plus partial y, 1, 2, times u2. So the question is, what is u1 and u2? Well, okay, so your direction vector is always going to be bumped down a direction, right? So, here we're dealing with just x and y components in the xy plane. So we can imagine that our unit vector is going to be in the xy plane, and it says that it's going to make an angle with pi over 6. Alright, so here's, I mean that's not really to scale, but so here's pi over 6. And the question is, what is u1, our x component of that angle, and what is u2, our y component? Okay. Now this is where the unit circle comes in handy, right? This is part of the reason why you had to memorize a unit circle way back in the day. Because the unit circle is really nice. It gives us components for unit vectors, right? So remember what the cosine of pi over 6 is. Cosine of pi over 6, or the cosine of any angle, is going to be adjacent over hypotenuse, and our hypotenuse on the unit circle is always going to be 1, right? We want this to be a unit vector. That's the whole thing. We want the magnitude of the vector to be 1. So anyway, on the unit circle, this guy is our cosine, right? Cosine of pi over 6 is equal to u1 over 1. So cosine of pi over 6 is just equal to u1. Right, multiplying both sides by 1. So the cosine of pi over 6 is root 3 over 2, and therefore u1 is root 3 over 2. In a similar way, the sine of pi over 6 is 1/2, so our u2 is going to be 1/2. So those components make up our unit vector that make an angle with pi over 6. Okay, so let's write that down here. u1 is root 3 over 2, and u2 is 1/2. So now we have everything we need to figure out the directional derivative. Okay. Let's do it. Let's do it. Okay. First of all, we need our partial. All right, partial with respect to x, with respect to y, then we're going to plug in the points into our partials to actually get a slope. Okay, so partial with respect to x is going to be 3x squared minus, keep the first times the derivative of the second, plus keep the second times the derivative of the first. Okay. And then plus 0, right? Because the derivative of that is just 0. Okay, so this becomes 3x squared minus 3y. So let me rewrite that. So we have 3x squared minus 3y. Now my partial with respect to y, x cubed goes to 0, and then we have keep the first times the derivative of the second, plus keep the second times the derivative of the first, which is 0, plus 8y. Okay, so this just becomes negative 3x plus 8y. Alright. Okay, cool. So now that I have that, I just go ahead and plug in 1, 2 in for x and y in my partials. So this one is going to be 3 times 1 squared minus 3 times 2. And that's going to give me negative 3. Over here, I get negative 3 times 1 plus 8 times 2. And that's going to give me, let's see, 13. Okay, so putting this together with these two guys, I can plug everything into my formula up here. Okay, so this is my answer. What did I just find? The slope at the point 1, 2 on the surface, x cubed minus 3x. Okay, so we found this. This is the slope. That's what this is. This is the slope at the point on the surface in the direction. Remember, we have to give these slopes a specific direction. So in this direction. So that's what this is. I know it's a lot. The slope at the point on the surface and the direction. But that's what it is, okay? That's what this is. This is a scalar. Our directional derivative is always a scalar once we plug in our numbers for A and B. Alright, now let's talk about something interesting. More interesting. The gradient vector. Okay, so I'm going to define it, and then we're going to use it. So the gradient vector of a differentiable function f at the point AB is denoted by grade FAB, okay? We can also use this upside down triangle to denote the gradient. And this, the way that we say this is del. It's kind of like a sideways delta. But anyway, this is how it's defined. The gradient of a function is going to be the partial derivative of x, plug in ab, I, plus partial derivative of y, plug in abj. So the gradient is a vector. Okay, the gradient is a vector. The directional derivative was a scalar, right? We plugged in an a and a b value once we got our derivative, and we got a scalar, we got a number. The gradient is always going to be a vector. And so what you should notice is that what we have here, the directional derivative was equal to partial derivative of x times u1 plus partial derivative of y times u2. And so basically that's just the gradient dot u, right? Because remember, when we take the dot product, we multiply the corresponding components and add them together, okay? So that's just a new definition. So this is the third definition that we just mentioned of the directional derivative. So what does the gradient actually do? So the gradient vector is super useful because it's going to give us the vector for the steepest climb on a surface, okay? It's going to tell us where is the surface the steepest, and that can be useful for a variety of different reasons. The direction of the gradient is in the direction of the maximum slope of f. And finally, the magnitude of the gradient vector is the maximum slope of f at that point. So we can always find the maximum slope on a surface if we know what the gradient vector is. And again, I already mentioned this, but this is just other notation. This is the gradient of f. We say del f, all right? So this, again, gradient vector gives us the vector for the steepest climb on a surface. So I want to show you guys a animation. I found this online, and this is really neat because it shows the gradient vector. If you look at the bottom, the gradient vector is in black, the one that's moving, and it's sweeping out the plane, and it's showing you what direction the steepest tangent line should be in for a given point at that tangent line. Right, so you can see that the slopes are changing, and the gradient is going to show you which of those slopes, in what direction is the slope the steepest. It's basically telling you where to aim your tangent line to get the steepest slope. That's what the gradient does. Okay. Alright, so let's go ahead and do some computation examples here. We want to find the gradient vector of a function at the point 1, 1, and then we want to find the maximum slope at 1, 1. So we have this surface, and we have a point, and we're trying to find, first of all, where the tangent line should point, the vector, the gradient vector, and then we're going to actually find the maximum slope at that point by taking the magnitude of the gradient vector. Okay. So first thing is that the gradient vector, so the gradient of f at 1, 1, partial derivative with respect to x, 1, 1, I, plus partial derivative with respect to y of 1, 1, j. Okay. So let's go ahead and find our partials first. So partial with respect to x of our surface is just 1, right? E to the y, we're thinking of that as a constant. Partial derivative of y is just going to be e to the y, okay? Now, if I plug in 1, 1 for these, I can't plug in anything here, so this just becomes 1. This becomes e to the first, which is just e. And so I can find the gradient. The gradient is going to be 1, right? That's this part right here, 1i, don't have to write the 1, but anyway, plus ej. Okay, so this is my gradient. That was the first part of the question. And the second part, so what is this giving me? This is giving me the direction that the tangent line on this point, the direction of the tangent line to this point, where should the direction be so that it gives me the maximum slope at that point? Where should it be? That's this direction, okay? Now we can actually figure out what that slope is by taking the magnitude of the gradient. So this is the maximum slope. And so magnitude, again, I'm just taking the square root of the squares of the components. So this is just the square root of 1 plus e squared. So this is the maximum slope. Weird number, I know, but that's it. So that's how we deal with things like that. Okay, let's go ahead and do another example. I think this was one in your textbook. So we have this function fr of h, so we're two variable function defined by 2 pi rh plus pi r squared, and we're interested in the point 2, 3. We want to figure out the gradient, so we want to figure out the direction that the tangent line should point for maximum slopage. I think I just made that word up, slopage. But anyway, you guys hopefully see what I'm trying to say. Where should that tangent line point for maximum slopage? And then we actually want to find the maximum slope by finding the magnitude of the gradient vector. Alright, so let's go ahead and find the gradient vector. So the gradient, and again, you can use the del if you want. And actually, maybe I will here just to get you guys used to it. So the gradient of f2, 3 is going to be the partial 2, 3 I plus partial. Oh, and by the way, we're not using x's and y's, we're using r's and h's, so let's change that to fr, fh. Okay. Alright, so there's our gradient. So let's go ahead and figure out the partial with respect to r. So this time we're holding h constant, just like we do with x's and y's. So we have 2 pi rh, so this is going to be, keep the first 2 pi r times the derivative of the second, derivative of h is 0, we're holding it fixed, remember? Plus, keep the second times the derivative of 2 pi r, which is just 2 pi. Alright, plus 2 pi r for this piece when we take the derivative. Alright, so that clears, and this is just going to give me 2 pi h plus 2 pi r. So that is my derivative with respect to r. Now if I plug in 2, 3 in here, I get 2 pi, so r is 2 and h is 3, so I get 2 pi times 3 plus 2 pi times 2, so that's 10 pi. So that was one piece of information that I needed. Now let's go ahead and take the partial with respect to h. Alright, so that's just going to be keep the first times the derivative of h, which is 1, plus keep the second times 2 pi r, which is 0. And then plus 0, because derivative of pi r squared is 0 with respect to h. Okay? So I just get fh is equal to 2 pi r. Now if I plug in r, which is 2, right? So fh23 is equal to 2 pi times 2, which is 4 pi. Okay, so I have everything that I need, and all I need to do is plug this stuff into my gradient formula right here. Okay, so the gradient is going to be, so fr23 was 10 pi, so I have 10 pi I plus fh23 was 4 pi, so this is 4 pi j. Okay, so this is my gradient, and so remember, this gives me the direction of the tangent line for maximum slope, okay, at this point, 2, 3. So let's go ahead and find the maximum slope by finding the magnitude of the gradient. maximum slope at that point. I should be careful with that. So this is going to be the square root of 10 pi squared plus 4 pi squared. So that's going to be 100 pi squared plus 16 pi squared. So that's 116 pi squared. You can simplify it if you want, but this is the max slope at the point 2, 3 on the surface in the direction of a unit vector. Okay. All right. Okay, so let's see. What do I want to do next? Okay, let's go ahead and do this problem. So we have function of two variables, so a surface. We want to find the gradient at 0, 1, so the maximum, or the direction of the maximum slope, right? And let's go ahead and do that. So the first thing we need to do is find the partial with respect to x and partial with respect to y. So partial with respect to x, derivative of sine of x is cosine of x. Derivative of e to the xy, we have to use a chain rule. This is going to be e to the xy times derivative of xy. Keep the first times the derivative of second plus keep the second times the derivative of the first. So this is just cosine x plus y e to the xy. That's my partial with respect to x. Let's see. Partial with respect to y. So sine of x just basically goes to 0, right? E to the xy. So chain rule. E to the xy times, keep the first, x, times the derivative of y, 1, plus keep the second, y, times the derivative of x, 0. Okay, so this just becomes x e to the xy. Okay, so we have our partial with respect to x and our partial with respect to y. Let's go ahead and plug our point in to see what we get. So fx 1, it's going to be cosine of 0 plus 1 times e to the 0 times 1. Okay, so the cosine of 0 is 1. So we have 1 plus e to the 0 is 1. So we have 2. Okay, so that's going to be my partial with respect to x, plugging in 0, 1. Now my partial with respect to y. So x is 0, so all of this goes to 0. So it's just 0. Alright, so my gradient is just equal to 2i, right? Plus 0j, but we don't have to write that. Okay, so we're going to use the gradient to find the directional derivative of a surface at a point in the direction of the given vectors. Okay, so the first directional vector that we have is 1i minus 1j. And this is not a unit vector because the magnitude is not 1. Right, it's actually square root of 2. So we need to go ahead and find the unit vector, or a unit vector. So how can we do that? Well, I just mentioned that the magnitude of this vector that we were given is going to be square root of the squares of the components. So that's just root 2. And so to figure out the unit vector, I can just take my original vector and divide the components by root 2. So I have 1 over root 2i minus 1 over root 2j. So that is my unit vector. I'm trying to figure out the directional derivative. And I want to use the gradient definition. So I want to use this definition. That's what it's asking. It's saying, okay, go ahead and use this definition. This is the definition we're going to use right here. All right, so we just found u. Now we need to find the gradient at 1, 1. And so I just need to find the partial with respect to x, partial with respect to y. So the partial with respect to x is going to be 1, right? Just derivative of that guy. Partial with respect to y is just e to the y. So plugging in 1 into this guy, right? I don't have anything to plug in there. I just get e to the 1, which is e. Okay, so this is my my y component. This is my x component of my gradient. So the gradient is going to be 1i, remember gradient is a vector, plus ej. So now all I have to do is dot these two things, and I'll have my answer. So remember, when we take the dot product of two things, we're just multiplying the components, corresponding components, and adding them all up. So we should get a scalar. So, okay, so we have 1 over root 2 times 1 plus negative 1 over root 2 times e. So that is our dot product. And we just get 1 over root 2 minus e over root 2. So this is just 1 minus e over root 2. So this is the slope on the surface at this point in this direction. Okay. Alright, let's do the next one. We have another vector that's not a unit vector, so we need to find the unit vector. First thing we need to do is find the magnitude of the vector that's given. So square root of the squares of the components. So this is going to give me the square root of 1 plus 4, which is 5, okay? Now that I have that, I can divide each component by root 5 to get a unit vector. So my unit vector is going to be 1 over root 5i plus 2 over root 5j. So I just took my original vector and divided each component by the magnitude to get my unit vector. So I'm going to take this and put it in my pocket, and then I'm going to find the gradient. Okay? So I already... well, wait, I'm sorry. I already found the gradient. Silly. Okay, so we already found the gradient of the function at 1, 1. And that was 1 over root 2i minus, oh wait, no, it wasn't. It was not. The gradient, sorry, the gradient was, let's see, yeah, it was 1i plus ej. Okay, there was our gradient. Alright, so now we can take the dot product by just multiplying corresponding components and adding them up. Okay, so 1 over root 5 times 1 is just 1 over root 5 plus e, so we did this times 1, e times 2 over root 5. So adding them together, I get 2e plus 1 all over root 5. And this is my slope in this direction on this surface at this point. Okay. Let's go ahead and do one more. Let's go ahead and first find our unit vector. So we need to take the magnitude of the direction vector that was given. So that's going to be, actually let's relabel this. So we have 1 squared plus 3 squared, and we're taking the square root. So that's going to be root 10. So for my unit vector, I'm just dividing my components of the direction vector by root 10. So this is going to be 1 over root 10 I plus 3 over root 10 j. Okay? Alright, and I already have my gradient vector. The gradient was 1I plus ej. Okay. So when I dot these together to get the direction vector, or to get the directional derivative rather, to get the slope, again, I'm just multiplying corresponding components, 1 over root 10 times 1 plus 3 over root 10 times e. Adding them up, and so this is my slope, 1 plus 3e all over root 10. Alright, so suppose the gradient of a function g at 5, 6 is represented with this vector. Find the slope of the graph of g at the point 5, 6 in the direction of this vector right here. So since we're given the gradient and since we're given a directional vector, it makes sense to use the directional derivative definition that involves gradient. So we have the directional derivative of AB. This is going to be, and again, just, hammer this into your brain that this is the slope at AB in the direction of U. Okay, just hammer that in your brain. Okay, so this is equal to the gradient of FAB dot U. Alright, so we already know, well actually I should have maybe called this G. Let's do that actually. Too many G's. So we know what this is, right? It was given. So the gradient of G 5, 6 was given. It was negative 3i plus 4j. The only thing left to find is the unit vector. Now, the vector that was given, the directional vector, is not a unit vector. If we take the magnitude of that, we don't get 1. So we need to find a unit vector by using that magnitude. So first of all, the magnitude of this vector that we were given right here is going to be the square root of the squares of the components. So I believe that is root 68. Yeah. Okay, so that's root 68. And so my unit vector, I'm going to take my original vector and divide each component by root 68. And to figure out what my slope is, I have to find my directional derivative, which is this. So I'm just dotting these two together, right? I'm just multiplying corresponding components, adding them up. So grade dot u is equal to negative 3 times 2 over root 68 plus 4 times negative 8 over root 68. All right. So there you have it. That is going to be the slope at the point 5, 6 in the direction of this vector. Hopefully this video was helpful for you guys. Thanks for watching, and I'll see you guys next time.